Okay, for the last video today, let's prove the chain rule. So let's set this up a little bit. The chain rule has kind of a lot of requirements because you're chaining two functions together, and that sort of requires a little bit of finesse, right? The output of one has to be inside the domain of the other, and that all has to go into our assumptions. So the theorem, we've got a continuous inside function. So suppose f mapping A to B, AB to R is continuous. And differentiable at x. Suppose G mapping some interval into the reals is defined on I, a subset of f of AB. So the interval that G is defined on is contained in the range of f. That means that I can actually compose these two things together. And G is differentiable at y equal to f of x. So f is differentiable at x. We want G to be differentiable at f of x. Then G composed with f at x is differentiable at x with G composed with f prime at x equal to our chain rule. G prime at f of x times f prime at x. Okay, so there's kind of a lot of moving parts going on. I've got to take their derivative of two functions at the same time and see how they work together. Okay, so our proof. We want to rewrite things so that I can use theorem 4.4 again and make things easy on us. We don't have to do epsilon deltas that way. So let's look at f of t minus f of x over t minus x minus f prime at x, and we're going to define this to be u of t. Okay, so this function here, we want it to be going to 0 as t approaches x, so u of t has to go to 0 as t approaches x. And this is going to be a defined, so a colon equals says define u of t. Usually it's written the other way, but define u of t to be that thing on the left hand side. We're going to define a v of s in a similar manner, and that similar manner is g of s minus g of y. Remember, y is f of x, and s's have to be different than t's because they kind of live in a different domain. G takes values from a different domain, and this is s minus y and g prime at y. And we're going to define this thing to be v of s. Because g is differentiable at y, both of these things go to 0. So this goes to 0, and this goes to 0. This one as t gets close to x, and this one as s gets close to y. Okay. Now, let me do these again and rewrite things. So I've got f of t minus f of x. okay, is equal to t minus x times f prime at x minus plus u of t. So that's just the first equation. Moving to the right hand side, u of t still goes to 0 as t approaches x, right? And I've got that g of s minus g of y equals s minus y times g prime at y plus v of s. Okay. And we're going to use these to get our composition working. So the composition, g of f of t minus g of f of x divided by t minus x. This is what we need to take the derivative of. So we want to see what this does as t gets close to x. We need to rewrite this. This is equal to, well, s here comes from t. So this is, let's say s is equal to f of t here. So I can write this using this is that, so I can use the right hand side of that over here. So I've got that s minus y, and then I've got, sorry, it's not s, that's s is f of t minus f of x times g prime of f of x plus v of f of x over t minus x. So that's just taking this left hand side here, so I'm replacing this thing in blue with this thing here, knowing that f of t equals s and f of x equals y. So anytime I see an s here, s goes to f of t, s, this is an f of t, and pink, y goes to f of x, and y goes to f of x. Okay. Now we're virtually done, right? Because this here in the limit then so I've got g of f of t minus g of f of x over t minus x. This limit is equal to the limit as t goes to x of f of t minus f of x over t minus x times g prime of f of x plus v of f of t. Okay. Which is equal to, well, that's f prime at x times g prime at f of x plus this limit as t goes to x of v of f of t. But by continuity, as t goes to x, f of t goes to f of x. That's why we needed continuity for f. Times g prime of f of x plus, well, we've got the limit as t goes to x of this, but this goes to v of f of x by continuity of t, which equals 0 here. This piece goes to 0. And we get our chain rule that way. Okay, that was the last differential theorem I want to do today. We'll see some examples and get to the mean value theorems, continuity of derivatives, L'Hopital's rule on Wednesday, and then hopefully we get to Taylor's theorem on Thursday, and then we'll go back and see some sequences and some series of functions so we can deal with Taylor's theorem a little bit more thoroughly.